Okay, so I want to show one of the propositions proven by Levi Ben Gerson. I don't know if I'm saying his last name correctly, but he was a mathematician working in the end of the 13th century and the beginning of the 14th century, and he's one of the Jewish mathematicians that the book mentioned. And one of the things that I like about his method here, it's kind of one of the first times induction gets done, uh, kind of I like more precisely. Um, but as the book mentions, his way of doing induction is a little bit backwards from ours, and I'll explain this as we go on. Now, our proof, what we want to prove, is that let me use a different marker here. What we want to prove is this interesting fact that the sum of the first n integers, and then you square them, this squared, if you take all of these and then you square it, is equal to 1 cubed plus 2 cubed plus dot 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 plus all the way up to n minus 1 cubed plus n cubed. Now, from a modern standpoint, this kind of has induction written all over it as a potential way to be able to explain or to prove what's happening here, really is how I should say that. Okay, so here's what I want to start with. I'm going to begin by squaring this. So what I want to do is I want to sort of think about this as a sum with two terms. This is going to be one term, and that's going to be the second term. So if I look at 1 plus 2 plus n minus 1 plus n squared, and again, I'm going to think about this as being one term and that being another term, this is equal to n squared. Okay, then it's going to be plus this part squared. Let's do plus 2 times the two terms. So plus 2 times 1 plus n minus 1 times n, and then plus this term squared. So plus 1 plus all the way up to n minus 1 squared. And now we can see kind of where something like an induction hypothesis would get applied, because now this is just, that, but this sums up to n squared. Okay, so what I want to show now is I basically want to show that this is equal to n cubed. That's what I need to show. So that's what I want to do. I'm going to show that that's equal to n cubed. So why is that equal to n cubed? Well, n cubed is equal to n times n squared. Now, what is n squared equal to? Well, I can write n squared in the following way. I can write this as 1, the sum all the way up to n minus 1, and then the sum all the way up to n. Okay, and this is just a consequence. I'm not proving this, but this is just a consequence of this summation formula. For the integers 1 up to a certain number, use those summation formulas, and you can see that this is going to be equal to n squared. Okay, well, notice what can happen. I can distribute this n to that n. So I can distribute this n to that n, and this is going to give me n squared. And then I can have n times, I can distribute to both of these. But notice if I distribute the n to there, I'm left with 1 to n minus 1 here and 1 to n minus 1 there. In other words, it's just 2 times 1 all the way up to n minus 1 like this. And so this right here is equal to n cubed, but that's exactly what we have here. Okay, so then what it shows is that the sum of the first n integers squared is equal to this, but this part here is just equal to n cubed. So let me erase this. I'm going to get different markers for the next video because I think these are not the greatest. So this is equal to n cubed plus 1 all the way up to n minus 1 squared. Okay, now typically the way that we would have argued here is we would say assume that it's true for all integers up to n. In other words, the so-called induction hypothesis would be that this right here is equal to 1 plus 2 cubed plus dot 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 all the way up to n minus 1 cubed. He took a slightly different approach, which in my opinion, there's something about this approach that I like because it's sort of an iterative process. Because what we're saying now is we're starting with something of this form and we get n cubed plus that. And now we're just going to iterate this estimate over and over on this. And so now what we're going to get, if we apply the same reasoning to this, to this quantity right there, we're going to have n cubed plus n minus 1 cubed plus all the way up to n minus 2 squared. Now we can see we can iterate this over and over again until we get down to n cubed plus n minus 1 cubed plus n minus 2 cubed all the way down to 1 cubed, adding 1 cubed. So like I said, in my opinion, there's something very pleasing about this because you get to see this sort of iterative or recursive thing that's happening. In general, I'm not a huge fan of proofs by induction because I don't think they don't always illustrate very well what's going on. But something, I don't know, this is more a matter of personal taste, something about writing it this way and sort of talking about things more iteratively and recursively in this way, I don't know, makes it a little more palatable to me. It's also, just practically speaking, there have been times when I need to, prove statements like this to maybe, I don't know, a calculus class or a differential equations class or something like that, and they don't know what mathematical induction is, or most of them, nearly all of them do not know what mathematical induction is. The formal procedures and that sort of thing. But I think this right here is much easier to get a grasp on. The last thing that I'll mention is that as a textbooks, I think it was this textbook that mentions they didn't really have notation for something like the sum of integers up to an arbitrary integer or something like that. They just had to sort of illustrate the formula with a specific number and then say, okay, this is how the formula, this is the formula or this is the proof. So for example, the way that the book states proposition 42, I know this is our book because I'm reading it directly. The square of the sum of natural numbers from 1 up to a given number is equal to the sum of the cubes of the numbers from 1 up to the given number. So things have to kind of be written sort of expositorily like that. Okay. Anyways, so this, like I said, an important step. Kind of, we have the first kind of getting into a formal induction processes here. Though induction really had been going on long before that, but I think, like I said, I mentioned this for two reasons. One, I like the proof, and two, I just like the statement of this proof. I think it's a very interesting proof or a very interesting idea. Okay, so that is it for this video, and I will make some other videos and show them to you.